Good afternoon. My name is Allison Clune, and I'd like to welcome you to the IAQ Science webinar series hosted by the U.S. EPA's Indoor Environments Division. Today's webinar, The Human Forest, Volatile Chemical Products Contribute to Urban Air Pollution, will be presented by Dr. Matthew Coggon. Dr. Coggon is a research scientist at the Cooperative Institute for Research in Environmental Sciences, also known as CERES, and the Chemical Sciences Division of the NOAA Earth System Research Laboratory. He earned a PhD in chemical engineering from the California Institute of Technology in 2015. Matt's research is focused on understanding the emissions and chemical transformations of volatile organic compounds in Earth's atmosphere. His current work is focused on understanding how emissions from consumer products contribute to urban ozone formation. Thank you so much, Matt, for being here with us today. This webinar is being recorded and will be made available on the EPA website at a later date. Please note, this presentation reflects the opinions of the speaker and not necessarily those of the U.S. EPA. If you have a question during today's presentation, you can type it in the Q&A box on the left-hand side of your screen at any time. Questions will be read to the speaker for discussion at the end of the presentation. If you have any technical questions or comments, you can submit those inquiries through the Q&A box as well. We look forward to hearing from you. So Matt, thank you again for speaking today, and I'll hand it over to you to begin the presentation.
Great. Thank you, Allison, and thank you everyone who's joined online. Today I'm going to be talking about work that we've been doing at NOAA and at CERES to try to understand how consumer product emissions can influence air quality in urban areas of the U.S. I want to start by thanking a lot of the folks who've contributed to this work, and shown here are some of the key players in that research. Most of these folks are with CERES and with NOAA. And the big takeaway that I hope you get from this talk is that emissions from volatile chemical products or consumer products are as large as those from vehicles in urban areas, and they significantly contribute to the formation of urban ozone pollution. Now, I like to always start my talks with kind of a broad overview, and when we think about air quality, and that's what we do here at CERES and at NOAA, we typically think about how air quality has changed from the past and to the present. And if you think about air quality in the 1960s, back when if you were in Los Angeles, you may not be able to make out the mountains that were right behind the city, you'd think of air pollution as being mostly due to vehicle emissions. But over the years, we've significantly improved the technology to clean up the emissions from cars, and through successful regulations, we've reduced vehicle emissions significantly, such that today, if you were to go to Los Angeles, you'd find that LA is about 4 times cleaner than it used to be in the 1960s. Now, this is a huge success story owing to the cleaning of exhaust from cars. Now, despite these improvements, urban regions in the U.S. still have pollution problems. If you were to go to LA today, or perhaps other urban regions, there will be days where ozone and PM 2.5 exceed healthy levels. Now, many folks turn to mobile emissions as a control strategy. However, regulations of vehicle emissions are becoming less effective, in large part because vehicles have become so much cleaner. For example, work by Gary Bishop, who is a researcher at DU, has shown that NOx and hydrocarbon emissions for new vehicles are incredibly lower than they were from older vehicles. So if you were to go out into the urban environment and measure on-road vehicle emissions, you'd find that new cars, shown here on the right in this graph, do not emit nearly as many pollutants as older cars from the 1980s. And it's turned into this situation where only a small number of cars actually contribute to the majority of vehicle emissions in urban areas. So, for example, in Denver, only 10% of the fleet actually contribute 80% to the hydrocarbon and NOx emissions in urban environments. And so that just shows you how much cleaner cars have gotten. And so it's becoming difficult to argue that vehicles are the biggest contributor to urban ozone pollution because they've just gotten so much cleaner. And as more of these older vehicles come off the market or leave the fleet, we will only see reduced effectiveness of controlling vehicle emissions. And this is something that's been shown even more widely across the U.S. So if you were to look at satellite retrievals of NOx and CO emissions, you'd see that over the past decade, there hasn't been a drastic reduction in NOx and CO emissions across the U.S. And so in the early 2000s, we saw decreases in NOx and CO on the order of a couple percent per year, but then that stopped around 2010, and since then, NOx has been relatively flat across the U.S. Now, this is in part because cars have gotten so clean, so gasoline emissions are no longer contributing significantly to hydrocarbon and NOx emissions as they were back in the early 2000s, as shown by Gary Bishop. But then also, we find that off-road vehicle emissions, as well as emissions from residential homes and industrial combustion, have slowed in recent years. So again, what this is showing you is that traditional combustion sources are not cleaning up the same way that they used to be. And so this begs the question, what other things must we do to reduce urban ozone pollution? If we want to continue to reduce the impacts of ozone and PM 2.5 on air quality, what other sources could be contributing to this urban ozone issue that we have in places like Los Angeles and other parts of the country? Turns out that there are other sources of air pollutants that we haven't considered, sources that are not traditionally considered by either regulatory communities or by atmospheric researchers. And in 2018, colleagues at NOAA and Ceres found that in places like Los Angeles, consumer products can actually contribute significantly to the loadings of volatile organic compounds in urban areas. This work published by Brian McDonald in Science found that, for example, in LA, the amount of VOCs that you would observe are comparable to the VOCs that are emitted from typical combustion sources such as gasoline exhaust, gas fuel, as well as other fossil fuel emissions. And so this paper has led us to rethink what contributes to urban ozone pollution and what contributes to pollution in general. And maybe it's time to start thinking about the indoor environment as being a source of pollution in the same way that we thought about cars in the 1960s. Most of these consumer products are emitted in the indoors, and then they're exhausted to the outdoors through exchange with homes exchanging air with the outdoor environment. Now, this isn't something that's only been observed in places like Los Angeles. We've actually observed this in other cities as well, small cities like Boulder, Colorado, where we do a lot of our work. For example, in 2018, we published a paper where we show that there are specific markers emitted from consumer products that help us to constrain the emissions of things like personal care products. We found that D5-siloxane, which is a major VOC emitted to the indoor environment, can be emitted at rates to the outdoor environment at rates that are equivalent to, say, benzene coming from your tailpipe emission. Shown here on the left, for example, is a diurnal pattern showing that in the morning, D5-siloxane is emitted at a rate that's equivalent to benzene, and it decays throughout the day as it's worn off people's skin from the use of personal care products. We've linked these emissions to sources such as homes and from vehicles. So as people drive around, they emit D5-siloxane from their personal care products, and then that mixes with the urban air along with benzene. And like I said, this mostly comes from personal care products, and what we found is that about 20% of these emissions come from your hair care products, 70% can be attributed to deodorant emissions, and if you were to sum up all of the emissions of D5-siloxane in Boulder, you would find that about 3 to 5 kilograms per day are emitted in Boulder, and compare that to benzene, it's about 15 kilograms per day. So that gives you a sense of just how much this is being emitted. There's such a source of personal care product emissions that it's competing with emissions of things like benzene, something that we've typically thought as being an important contributor to air pollution. Now, this work has led us to question, do VCP emissions impact the air quality of other urban areas? And furthermore, what do these do to smog formation? So the work in Los Angeles and this work in Boulder, Colorado has shown that there are large emission sources, but how do these actually translate into smog formation, ozone formation, PM 2.5 formation? So to answer this question, we've followed up on this work to look at VCP emissions more broadly, and specifically we were interested in trying to understand, are there other regions where you can see these emissions, and then can you quantify the ozone formation? So we conducted an experiment that we called the New York Investigation of Consumer Emissions, and this was conducted alongside the Long Island Sound Tropospheric Ozone Study, which was led by members of EPA as well as other institutions across the U.S. to try and understand ozone formation in areas of New York City. This study was conducted in March of 2018 as well as July 2018. What we did is we packed instruments into a mobile laboratory, and we drove from Boulder, Colorado, all the way across the U.S. to New York City. In our van, we had a mass spectrometer that can measure hundreds of volatile organic compounds at very high rate, so that we can look at the fingerprint of volatile chemical products and compare that to traditional sources such as vehicle emissions. More specifically in New York City, we were stationed in Upper Manhattan at the City College of New York. You can see here that the City College of New York is in a very densely populated area of New York City. We chose this region because if you're going to see volatile chemical products, you would expect to see them where there are lots of people. We had our instruments set up in the basement of an engineering building, and then we had a long inlet to the top of the roof where we could measure these emissions for multiple weeks. In addition to this ground sampling, we drove our van around the New York City region. So on the right, you'll see a map colored by population density. The red trace is where we drove our van. So we drove our van from rural New Jersey, for example, all the way into the densest parts of Manhattan, and then all the way out to Long Island. And the idea is if you are to see volatile chemical products, you would expect to see them in the most densely populated areas, and we can compare that to regions where there are less people and hopefully understand their impact on urban air quality. Now, there are lots of emissions associated with volatile chemical products. I've talked about D5-siloxane as coming from personal care products, but one component that's often considered important by regulatory agencies as well as by indoor air quality researchers is fragrances. If you were to measure the air of the room that perhaps you're sitting in right now, you would find that fragrances can contribute significantly to the concentrations of monoterpenes. And the reason is because monoterpenes are extracted from limes and from pine sources and added to fragrances for their pleasant smelling properties. And in fact, if you were to measure the head spaces of many different types of consumer products, you'd find that there's consistency in the types of monoterpenes that you would measure. So for example, shown here are data from Ann Steinemann's work, where if you looked at all of the monoterpenes that could be emitted from a fragrance consumer product, you find that about 50% is mostly limonene. So there's a signature of anthropogenic monoterpenes that perhaps if you were to measure an urban environment, you may see these enhancements alongside population density. And so we are interested in going to New York City to try and see, do you measure fragrance consumer products, and how do these impact air quality as well? And from Brian McDonald's work in LA, there's a question whether these are a significant emission. And if you dig into the inventory work that Brian did, you'll find that the emission rate of fragrance consumer products can be quite large. To compare that, I'm going to show you monoterpene emission rates estimated from Brian's work compared to what you might expect from a dense forest. So typically monoterpenes come from biogenic sources. Like I showed you, we extract them from biogenic sources and add them to fragrances. But in a natural environment, such as a dense forest in the southeast U.S., you might observe monoterpene emissions of about 30 moles of carbon per square kilometer per hour. If you look at Brian McDonald's inventory in Los Angeles, you'd find that fragrance consumer products could emit as much as 15 moles of carbon per square kilometer per hour of monoterpenes. So there's a question, is there really a significant source of anthropogenic monoterpenes in U.S. cities, i.e., is there a human forest associated with volatile chemical product usage? So I'm going to show you data from New York City to convince you that, yes, there is a large source of anthropogenic monoterpenes. And I'm going to show you this by looking at spatial distributions of VOCs from our drives in New York City. First, I'm going to show you the spatial distribution of D5-siloxane. Now, remember that D5-siloxane is our personal care product tracer. And so if we observe significant emissions of D5-siloxane in urban areas, we know that that region was influenced by consumer products. Here again is a map of New York City, colored by population density. On top of that, I'm going to put our drive track, and I've colored it by D5. And what you can see is that as we drive throughout the metropolitan area, there are enhancements of D5-siloxane in these really densely populated regions, primarily in Manhattan. To show this more clearly, I'm going to take these data and I'm going to bin them by longitude. So in each region, you can average the concentrations, say in rural New Jersey, average the concentrations in downtown Manhattan, as well as those in Long Island. And that's shown here as these white squares. And you can see clearly that as we drive into New York City, there's this enhancement of D5-siloxane. And then it decays away as we go further into Long Island. You can do the same analysis with the population density data beneath our drive track. And what you find is that there's a very good correlation. So in areas of densely populated, in areas of dense population, there are more D5-siloxane emissions. Let's do the same analysis, but now with monoterpenes. And you can see that there's a very similar enhancement. Now, rural New Jersey is an area that has a lot of monoterpene emitting trees, but we don't see enhancements of monoterpenes. Now, I'll mention that this was conducted in winter when we don't expect a lot of monoterpene emissions, but what you do see is a lot of monoterpenes in New York City, again suggesting that there's an anthropogenic source of fragrance consumer products. We can then look at how the fingerprint of monoterpenes change as you go across the metropolitan area. So the drive data are with a proton transfer mass spec. It cannot tell you exactly what type of monoterpenes these are, but we did have a GC mass spec on our van, and so that using this data, we can actually tell you what kind of monoterpenes were we measuring in these different regions. These pie charts here show you the distribution of monoterpenes in different areas. So on the left, these are the distribution of monoterpenes from the biogenic areas in New Jersey. The center, these are monoterpenes measured in downtown Manhattan, and to the right, these are monoterpenes measured in Long Island. And what you see is that the distribution is drastically different. In New Jersey, most of the monoterpenes are alpha and beta pinene. In downtown New York, it's mostly limonene. And then out in Long Island, we again have that domination of alpha and beta pinene. Okay? And so because this distribution is different, it tells us that there's different types of monoterpenes being emitted, and we can link this back to our anthropogenic fingerprint. So where we drove in central New York City, again, looks a lot like the monoterpenes that I showed you earlier from consumer products. It also looks a lot like the monoterpenes that you would measure in an indoor environment. So shown to the right are the average profile from residences as reported by Logue et al. And again, you can see that residences are mostly dominated by limonene, and in New York City, that's what we see. So that shows you that we're measuring an anthropogenic fingerprint. Outside of New York City, the monoterpenes that we measured in New Jersey as well as Long Island look a lot like the monoterpenes that you would expect from pitch pine. This is from Guerin et al. And shows that again, outside the city, alpha and beta pinene are showing you biogenic sources. Okay? So what we're seeing in New York City is something that looks like an anthropogenic source. Now we want to know how much of this is being emitted. How many anthropogenic monoterpene moles per day are being emitted, and how is that comparing to the natural source outside of New York City? To do this, we've done an extensive amount of modeling, and I'll talk a little bit more about this later in this presentation. But what you can do is you can compare our drive across New York City to the amount of monoterpenes that you expect from a 3D model. So we use WRF-Chem to simulate air quality. And so what I'm showing you here is our drive track in black across the New York region. This is during summer, so this is during the summer portion of our experiment. And in yellow is Manhattan. Now in WRF-Chem, if you only had a biogenic source of monoterpenes, that's this dotted blue line here, you can see that we can't recreate the observed monoterpene concentrations in Manhattan. It's only when we add an anthropogenic source that scales with population density that we can actually recreate the drive across New York City. Now, how much did we have to add? How many monoterpenes did we put into this model? Well, if you were to integrate the total monoterpene flux across Manhattan, you'd find that we had to add about 70 moles of carbon per square kilometer per hour in order to recreate this profile. So think back to the previous slides where I showed you the biogenic flux. That was about 30 moles of carbon per square kilometer. What our data is showing is that in New York City there is an anthropogenic flux that's equivalent to or greater than the natural flux for an area the same size as Manhattan. And so that just shows you that there's a significant amount of anthropogenic monoterpenes being emitted in a place like New York City. Now, I've talked a lot about fragrances, and I've talked about these because they're uniquely tied to VCPs, but we observed other VCP markers across urban areas in New York City as well as other areas of the U.S. And so it's not just that we're seeing only one type of molecule, we're seeing many types of molecules that tell us that VCPs are important in urban areas. And so I'm going to show you an analysis that helps us to understand all of the types of VCPs that are emitting in urban areas. And I'm going to start this by showing you, for example, the drive across the U.S. colored by D5-siloxane. All right, so in every urban area that we drove into on our way to New York City, we saw large enhancements of D5-siloxane. So you can pick out, for example, Denver, Omaha, Chicago. You can see Pittsburgh, and then again New York City. And if you think about how densely populated these areas are, you can kind of see that there's some relationship between how big a city is and how much D5-siloxane we see. Well, we had this hypothesis that if you wanted to identify other VCP markers, perhaps there's a relationship with population density. So our hypothesis is that traffic emissions increase with population, but they plateau in large cities due to road volume restrictions. Okay, and that's been shown in studies of city size, that as you grow a city, there's only so many cars that you can fit on a road. But people emissions scale linearly with population density. So as the population grows, VCP emissions should increase with population density. So therefore, if you were to see VCP emissions in populated areas, you would expect that the VCP to traffic ratio should increase with population density. And so using these data from all these cities across the U.S., we can look at the ratio of all the VOCs that we measure with our proton transfer mass spectrometer. We can ratio these to benzene, and we can see, is there a correlation with population density? And if there is, this tells us that the molecule that we're measuring is a VCP tracer. And I'm going to show you that this actually does work. So I'm going to start by showing you that there's not really a correlation with molecules associated with traffic. So for example, toluene, C8 aromatics, and C9 aromatics, when measured in urban areas, are typically associated with traffic. You can see that their ratio to benzene does not have a strong correlation with population density. Now, each of these markers here indicate a city. So here on the low end of population density, we have Denver. Here in the middle, we have Chicago. And then on the right, we have New York City separated out by its boroughs. We do this because New York City has a huge range of population densities. And so this gives us more statistics so that we can look at these relationships. Now compare this to D5-siloxane. And what you see is a very strong population density relationship. Much like what we showed just on a spatial, in New York City, we showed the spatial correlation across New York City. Again, now across the entire U.S., we can see that there's a relationship of how much D5 there is compared to population density. Now, we also see this with monoterpenes, again indicating that there's fragrance use in all the cities we measured during our drives. Within each of these plots, I'm also showing you a pie chart showing the emission inventories, estimates of where these emissions are coming from. So the sources are at the bottom here. So in blue, these are personal care products. If you see pink, that's adhesives, greens, fragrances, etc. And so in D5-siloxane is primarily coming from personal care products. That confirms that this is a good tracer for personal care product emissions when measured in an urban environment. Monoterpenes, again, are mostly coming from fragrances in these emission inventories. Now, there's other molecules. So D4-siloxane, that shows a really good correlation with population density. D4-siloxane is mostly coming from adhesives and insecticides. So that's showing you that adhesives are affecting the air quality in all these urban areas that we measured. For insecticides, we find that there's a good correlation of p-dichlorobenzene. P-dichlorobenzene is one of the main components in mothballs. And so you can see there, that molecule has a good correlation with population density, showing that insecticides have some relationship with how many people there are in an urban environment. Parachlorobenzotrifluoride in emission inventories mostly comes from solvent use, from coatings. So these are solvent-borne coatings. And you can see that there's a weak correlation with population density. We don't fully expect population density, a population density relationship for parachlorobenzotrifluoride, since solvent-borne coatings are primarily used in construction projects, and that may not scale with population density, but we do see that there's maybe a weak relationship. The most surprising for us was ethanol. So ethanol traditionally is thought to come from vehicles. Again, previously I showed you that there aren't very good correlations for vehicle markers like the aromatics, but for ethanol there's this very strong correlation with population density. Ethanol comes from many different sources in emission inventories, so it can come from personal care products, adhesives, coatings, and waterborne coatings, solvent-borne coatings, at almost equal proportions. So ethanol seems to come from everywhere, but is mostly driven by the use of personal care, from the use of volatile chemical products. So the point here is that we can measure many different markers for consumer product emissions. And now what I'm going to show you is that those markers allow us to constrain emission inventories to assess how much must volatile chemical products be influencing urban environments. So here I'm going back to New York City, and what I'm showing you is how the inventories that we've developed compare to our observations in New York City. So on the left, we have VOC to CO ratios for the emission inventory that we've developed for New York City. And on the bottom, I'm showing you VOC to CO observations that we made during the winter time of this New York City experiment. And what you see is that if we only consider fossil fuel emissions, we can't recreate the observations for a number of the molecules that we measured, primarily coming from VCPs. So for example, we can't recreate ethanol observations. We can't account for acetone. We can't account for the C9, C10 alkanes, which also come primarily from consumer product emissions. Now, if we include the VCPs into the emission inventories, you can see that we can start to recreate the observations very well. We can account for most of the ethanol that we observed. And then we can also account for all of these tracers that I showed you earlier. So dichlorobenzene, PCBTF, D4, D5 siloxane, we can use these markers to show that by adding VCP emissions, we can account for the majority of the trends that we observed in many, many different species. And so this shows that VCP emissions do impact the air quality of New York City significantly. And I don't have this in the presentation, but on average, about 70% of the VOCs that we measured in New York City came from VCPs. So the breakdown here is about 70% from VCPs, 30% from traffic. And so VCPs are significant, and they're ubiquitous. So we showed you that we can measure these across the U.S. So the next question is, do these VCPs contribute to urban smog formation? We see a large emission source, but are they actually contributing to ozone formation? So when we were in New York City, we observed a number of high ozone events. We were there during a period where ozone reached about 100 ppb in New York City, and then downwind, ozone reached 120 ppb in the surrounding areas along Long Island and northern New York. And so what we can do is we can try to model these ozone episodes and try to understand how much of this ozone was due to the emissions of volatile chemical products. So what is the contribution of VCPs? To do that, we used two models. I mentioned this previously that we used WRF-Chem, but we also have a 0D box model that allows us to try to understand the VCP impact on ozone. So WRF-Chem was set up across the U.S. We had a 12-kilometer grid that covered the entire United States, and then a finer resolution grid, 4-kilometer, over New York City. The purpose of this model was to quantitatively evaluate ozone pollution in New York City. Now, it's hard to do a lot of sensitivity analyses with a 3D model because of the computational resources it takes. So we use the 0D box model to evaluate what components of VCPs contribute to this ozone, these ozone exceedances. And so using a simplified model constrained by the 3D model, we can start to understand what are the largest ozone precursors. Now, we did a lot of work to try and validate this model. So we used the emissions inventory that I showed you previously. We also compared this model to meteorological parameters, NOx emissions. We also have the model constrained to our isoprene observations measured across the U.S. We also compared it to formaldehyde, and then again, ozone measurements. And in all cases, the model performs very well. I'm only showing you here how the model performs with respect to ozone. But in general, WRF-Chem is doing a very good job across multiple sites in New York City. In general, we have a low bias, so it's maybe overestimating ozone by about 2 ppb, and then it has a very good correlation coefficient of about 0.92. So this is just to show you that we're doing a good job in capturing ozone with WRF-Chem. So with this model doing a good job, we can start to look at sensitivity analyses to try and understand how much of this ozone that we're observing during these exceedances come from VCPs. So what I'm showing you here is a map of New York City, and these are the WRF-Chem results, 8-hour ozone on the highest ozone exceedance on July 2nd. I'm showing you the amount of ozone in 3 regions on the right, and we're comparing these to observations in New York City, shown here by these set of bars to the far left. In the middle, I'm showing you, or sorry, this is the regional background, shown by this minimum here in the upper right corner of the map. Here are the model predictions in downtown New York City, and then on the right is ozone observed at a downwind site, and this is where the maximum ozone was observed in this region on July 2nd. Okay. I'm first showing you what the picture looks like when we only have emissions of biogenic VOCs and anthropogenic NOx. And in general, the regional background is explained very well by these two emissions. So if you only had biogenic VOCs and NOx, you could explain the regional background fairly well. But you can't explain the observations in New York City or at this downwind site where we observed maximum 8-hour ozone. Okay? So now what we'll do in the model is we add in fossil fuel emissions. So if we add in fossil fuel emissions, you can see that we start to explain the ozone a little bit better. So we can start to see that in New York City. We're getting closer to the observations. And then at the downwind max, again, a little bit closer. So adding in fossil fuel VCPs gets us a bit closer to this ozone maximum. And then if we add in VCPs, ozone increases a bit more. If you compare all of the ozone monitors in New York City, that's shown by these white circles here, with the WRF-Chem model output, you can see that there's actually very good spatial agreement. So the model, again, just showing that it's doing a good job in capturing ozone more widely. This is also showing that you need anthropogenic VOCs in order to explain the observations. Now, typically when we think about ozone exceedances, we often think about NOx being the primary driver of high ozone events. But what our results are showing is that anthropogenic VOCs also play a significant role, and that you need these emissions in order to explain high ozone events. Now, using the box model, we can start to try to understand how much of this ozone comes from VCPs. You can kind of see this as we increment from fossil fuel emissions to VCPs, but it's actually most clear in the box model. So using the box model, we can essentially treat this as an air mass that's advecting north, and we can look at, as the air mass moves from New York City to that high ozone region to the north, how much of the ozone is coming from biogenic emissions, how much of the ozone is coming from fossil fuels, how much is coming from VCPs. So what I'm showing you here is distance that the air mass has traveled from Central Park to the region where we had that high ozone peak downwind of New York City. And you can see as the air mass advects north, half of the ozone can be attributed to biogenic VOCs, and half can be attributed to anthropogenic VOCs. And if you were to look at only the anthropogenic component, about 30 to 40% of the ozone came from came from VCPs. So that's showing you that our box model suggests that VCPs are contributing to this ozone exceedance, and at a contribution that's nearly equivalent to what you would expect from fossil fuel VOCs. If you were to look at the the ozone from VCPs more carefully, you can start to see what components of VCPs are contributing to this ozone exceedance. So what I'm showing you here are sensitivity analyses in the box model by turning on and off individual VOCs from the VCP categories, and then apportioning these based off of where they came from. And what you can see is that VCP emissions generally are, the amount of ozone coming from VCPs is generally spread amongst about 4 categories. It's mostly coming from personal care products, cleaning products, coatings, and adhesives at pretty much equal proportions. And what's interesting is that if you were to look at all of the individual components of VCPs, you find that there's 2 that are the biggest contributors. Monoterpenes, those anthropogenic monoterpenes that we talked about earlier, account for about 10 to 15%. And then ethanol. Ethanol, which we showed earlier, comes from all types of VCPs, contributes about 10%. And so the 2 of those make up about 25% of the VCP ozone. The rest can be attributed to oxygenates like glycols, aromatics, and then alkenes. So this is showing you that VCP ozone is important, and that there's specific molecules that are contributing to VCP ozone. The next question that we had is if you were to if you were to look at sensitivities to VOCs more widely, how much would reducing VOCs or reducing NOx lower or improve ozone in the New York region? And so we calculate ozone isoplus using our box model. And what you can see here is as we decrease or increase VOC and NOx emissions, you can see that the New York City at the 8-hour ozone maximum is actually NOx saturated and VOC sensitive. So in our model, what this is suggesting is that if you were to reduce VOCs from VCPs or fossil fuels, there's some sensitivity to that, and that was shown in the 3D model as well, implying that this region has some VOC sensitivity. We can show this again with the box model by looking at ozone sensitivity across the whole New York City region. So shown here is if we take our model and we decrease VOCs by 50%, how does ozone respond? If we do the same thing by decreasing NOx, how does ozone respond? And what we find is that if you decrease anthropogenic VOCs by 50%, there's a reduction in ozone within 40 kilometers of the New York City region. On top, I'm showing you population density, showing you where most of the people reside. And so in areas where there are lots of people, there's VOC sensitivity in our model, implying that if you were to reduce VOCs by 50%, it would be more effective than reducing NOx on a local sense. On a regional sense, as you go further downwind, reducing NOx by 50% has a bigger effect than reducing VOCs. The point that we're trying to show you here is that that anthropogenic VOCs, as we showed with the 3D model, do matter, and that by reducing anthropogenic VOCs, you can have a big impact on local ozone production. Okay, so I'm going to conclude with some of the key points here that anthropogenic VOCs, both from VCPs and mobile sources, significantly contribute to ozone formation in the New York City area. This is something that's not really considered. It is not typically thought to be an effective control strategy. Typically, NOx reduction is considered, but our results show that you can do a fairly good job by also potentially reducing anthropogenic VOCs. NOx reductions matter for regional ozone formation, but again, VOC reductions could be important. And then finally, VCPs are ubiquitous in urban regions, and monitoring species such as ethanol or monoterpenes could be an effective way of understanding the VCP impact on ozone. Now, this work has drawn the attention of NOAA in general. So Brian's work, as well as the work in New York City, has led us to question: is this something worth exploring more widely? So NOAA is actually going to continue to do this work in 2021 in a campaign called the Atmospheric Emissions and Reaction Observed from Megacities and Marine Areas, or AROMA. This is going to happen in the summer of 2021, where we're going to pack instruments onto a NOAA P3, and we're going to measure the trace gases and particles from U.S. cities around the U.S. We're also focused on marine regions because NOAA has become interested in understanding, again, the sulfur budget off of the coasts of Los Angeles, and so we're trying to link these two experiments into one, where we can start to understand air quality in urban regions and in marine areas. This is mostly a plug in case anyone on the line is interested in learning more or perhaps being involved. But the aircraft's going to be located in two areas. First area is going to be in Los Angeles, where we're mostly going to be flying in LA, and then to other major areas such as San Francisco. We'll also be stationed out of Portsmouth, New Hampshire. Shown here is these circles show the range of the P3. We'll sample regions in Chicago, Toronto. We'll go down to New York City as well as DC. And then the color scale here shows you monthly concentrations of DMS. The point here is to show where we'll also fly to try and understand these marine environments. We're going to go in July. Typically, the ozone season is in June to August. What I'm showing you here is how the ozone season has changed over time. So from the 1980s until today, the ozone season has gotten earlier and earlier. And now in areas like New York City and in Los Angeles, the ozone season is sometime in July. So we'll fly out into these regions about the July to August timeframe. The P3, like I mentioned, is going to be packed with instrumentation. This is just to show you that it's going to be one of the most extensively instrumented aircraft campaigns ever to go out to measure urban environments. So if you're interested, there will be a white paper coming out shortly describing this field campaign in more detail. But just to show you, this would be a lot of interest to perhaps folks on the line. With that, I'm going to stop and thank you all for listening, and I'm happy to answer any questions.
Thank you, Matt, for that excellent presentation. We do have quite a few questions here, so I'll just start off with one of the first ones. Are there any specific types of personal care products that emit more or less VOCs?
That's a good question. There seems to be, it seems to be fairly ubiquitous in the inventories. The inventories don't really go into that much detail about specific types of personal care products, but so there's not that granularity in the emission inventory. So that's hard to say, but as we measure personal care products, for example, in more detail, we may be able to find new tracers that link them to specific types of different types of products. So D5-siloxane, as we showed, is mostly in deodorants and hair care products. Perhaps we'll find something, in makeup. Perhaps we'll find something in spray type personal care products. But that's an open question. So hopefully Aroma and other campaigns that are investigating the urban environment can answer that question. But as of now, that's a really difficult one to answer.
Great, thank you. We do have a question about a specific type of product. Is the increasing popularity and use of essential oil diffusers a significant concern? That's an interesting one. So I typically think about our use of fragrances, and we use fragrances in many different environments and in many different ways. So think about in your home what type of things might be fragrance. So we have fragrance diffusers. But we have fragrance trash bags. What's the point of a fragrance trash bag? So it's everything's fragrance these days. And I don't necessarily think that there's one or the other that should be of concern. It's mostly just thinking about the use of fragrances, how much you use, and how that might be contributing to air quality. And I have to note that one of the reasons that there may be so many fragrances today is because they're useful not only in their smell but also as properties of degreasing. So limonene, for example, is a great degreaser. That's why you find it in cleaning products. And it's in the 1980s, 1990s, when there were efforts to reduce hazardous air pollutants like benzene and toluene, there was consideration of replacing these in products with something that's more green and friendly. So you can reduce aromatic content in cleaners with limonene. And so, one of the reasons that there's so much use of this, one of the reasons, we have pine sols and we have lemon-smelling cleaning products is because we added monoterpenes to reduce the hazardous pollutants that were typically added to these products. So there was a benefit to doing that, but now today, we have to rethink how might these be contributing to air pollution. And so diffusers, they may be one component, but there's lots of different fragrance
consumer products, and it's partially for a good reason that we have these things.
Great. Another question about products. You talked a lot about siloxanes in the beginning of the presentation. How are siloxanes, or what are they called on ingredients labels?
So there's cyclopenta, there's a big one, cyclopenta-methyl-siloxane. They're called dimethicone. There also can be called cyclodimethicone. And it's not just D5-siloxane that's in these products. There are linear siloxanes. And often if there's a silicone component to your products, it would typically contain siloxanes.
Thank you. Another question, switching gears a little bit. When you consider consumer products VOCs, are you looking at just the total emissions, or do you look at the impact of these emissions based on their maximum incremental reactivity?
Yeah, so in the modeling that we did, we haven't considered MIR. Mostly we're trying to understand, in New York City as a base case region, how much might these contribute? So the ozone contributions that we look at are model related, but that does have some relationship to MIR. I will say that that during the period that we were making these measurements in summer, there was very high OH concentrations, so it was about an order of magnitude greater than the average OH concentration. So it was like 1.7 times 10 to the 7 molecules per cubic centimeter. And so that means that the chemistry was very hot. And in a way, it kind of relates, the distribution that we look at kind of relates to MIR. So as you cook the emissions, this is kind of like the maximum ozone that you would expect from these measurements. If you go closer to the city, the distribution of ozone precursors looks more like OH reactivity. So there's a changing scale as you go further downwind. But our results look more like maximum incremental reactivity. That graph where I showed you the distribution of VCP components to the VCP ozone, that looks more like MIR than it does OH reactivity.
Great. So a couple of questions about different sources that might contribute to some of these substances. Could substances like ethanol and acetone also be driven by human population, since each of these substances are produced in the body and expelled by the body?
That's a great question. We haven't done the back of the envelope calculation to estimate what those emissions would be. And perhaps that could be a component of this. I'm not too familiar with that research, the physiological components of these emissions. But yeah, that's certainly something that could also be a component of that. What we find, though, is that we can explain the acetone and ethanol emissions in the inventory by including VCPs. So we don't need to invoke a people emission in order to explain acetone and ethanol in urban environments. We can do that just by including VCPs. So while there may be an effect, we haven't tried to quantify it, but it doesn't seem like it would be drastically bigger than the VCPs.
Excellent. Let's see, another question related to ethanol. Could ethanol be coming from gasoline, since it's added at approximately 10%?
Yeah, so our results show that there is a transportation component to ethanol, but in New York City we find that 70% of it is coming from VCPs. And so when we showed those population density relationships, again, if a molecule has a population density relationship, it is mostly driven by VCPs in our data set. We showed, for example, that aromatics which typically come from vehicles, don't have a population density relationship, but in our measurements, ethanol did. And so while there is a component of gasoline emissions influencing ethanol, it appears that across the cities that we measured, ethanol was mostly driven by VCPs and not from traffic. And, you know, New York City, it was a 70-30 split. In LA, it was about a 50-50 split. So, you know, that's just showing you how much VCPs are contributing to this.
Thank you, Matt. Another question about a source of emissions. What kind of emissions might come from dryer vents?
Yeah, Ann Steinemann has shown that there's a lot of monoterpenes emitted from laundry products. So we would expect monoterpenes to come from dryer vents. You know, in terms of other molecules, that's certainly something that we need to look into more. I know that in dry cleaning processes, nitromethane is used as a solvent. And so there could be, in more of an industrial cleaning process, you may see nitromethane emissions. But in terms of other molecules, we're not too sure yet. So, you know, we use these population density relationships that I showed previously to identify VCPs. And as we make more measurements, we may start to identify molecules that we hadn't seen before. And so perhaps as we do more of this work, we may identify molecules unique to laundry products. And I think the viewer probably noticed that we didn't have a marker for laundry products in our list of markers quite yet. And that's one that we still need to hunt down. So that would be certainly something for us to look for in aroma, for example.
All right, thank you, Matt. I have a question here. Is there any data for methyl isobutyl ketone levels in urban areas or residential indoor values? Or perhaps more generally, how do the VOC levels indoors compare to outdoors?
Yeah, that's great. So my understanding with the indoor environment is that concentrations are often 10 times higher in the indoor environment than the outdoor environment. So if you look at the indoor to outdoor ratio, VOCs are often 10 times higher on average than the outdoor environment. And I know people on this line know a lot more than I do about this. So, you know, when I think of the indoor environment, I almost think of it as a little engine that could be, you know, spewing out VOCs into the outdoor environment, much like how we think about how we've thought about traffic emissions in the past. To that specific molecule, I haven't looked too much into it, so I'm not aware what its concentrations may be in the indoor or outdoor environment, but certainly something to look for. But we haven't really looked at that one specifically.
Excellent, thank you. Another listener asked, how do VOCs and VCPs lead to the formation of ozone exactly?
Yeah, so the recipe for ozone formation is you need VOCs, NOx, and sunlight. And so all types of VOCs contribute to that soup, contribute to that recipe. So, you know, typically in like the Northeast, for example, isoprene, which comes from biogenic sources such as trees, is one of the dominant sources of ozone. But then traffic emissions can do the same thing. So as long as you have, and then VCPs as well, but as long as you have a mixture of VOCs and NOx, that's what leads to ozone. So if you have those three components, NOx, VOCs, and sunlight, you will create ozone. And it's through a complicated, you know, complex set of reactions. It's hard to discuss over the phone, but you know, as long as you have those three components, you'll make ozone. And so it also depends on the reactivity. So how quickly do those molecules react in the atmosphere? So the faster a molecule reacts, typically you'll get more ozone, and or more local ozone, I should say. And so the reactivity of VCPs and traffic emissions are about equal. So that's perhaps one reason why local ozone formation is kind of a 50-50 split between traffic and VCPs. Even though you have more VCP emissions, the reactivity of those two sources are comparable. So it's a bit complex, but there's really, as long as you have VOCs and NOx, you can make ozone.
And a related question, are VCPs important for ozone transport from one state to another?
I would say that certainly there's potential. What we showed is that, and I know I went through it a bit fast, but on a regional scale, at least in New York City, the amount of ozone that you formed was largely influenced. It became what's called NOx sensitive, and what that means is that NOx had a bigger influence on ozone than VOCs on a regional scale, and that's in part because there's a lot of biogenic sources on a regional scale. So as you go further and further away from New York City, the amount of ozone that you form becomes more heavily influenced by the number of biogenic sources. So it's difficult to assess how much of the VCP ozone that's formed in New York City, how much of that is contributing to the ozone perhaps you would see in, say, Connecticut. That, is kind of a difficult question to answer right away, but something that we could investigate with our models. But my first guess would be that most of the ozone formed downwind, as you go further and further downwind, would largely be influenced by the biogenic emissions. So, in our study, we're thinking mostly on the local scale, but there's certainly, opportunity to look at that more intensely with further modeling.
Great. Our next question, a listener asked, assuming the day-to-day emission of VOCs or VCPs over urban areas is not cumulative, what is the reset period for the emissions to dissipate, and how does nature wash them from the atmosphere?
Yeah, that's a great question. Can I move these slides around?
Yeah, no problem.
Okay. I think the D5-siloxane trend kind of highlights that. So in Boulder, for example, most of the emissions of D5-siloxane happened in the morning, and then they dissipated throughout the day as they wore off our skin, right? So as your deodorant and hair care products evaporate, they eventually get washed out and are ejected downwind. And that happened on a time scale of about 9 hours. So the big emissions from the morning application of personal care products kind of dissipated locally on that time scale. The next question is, how do these accumulate downwind? That's a bit more complicated and depends on the reactivity of the VOCs. So D5-siloxane, for example, is not super reactive in the atmosphere. So once it's emitted, it's not going to quickly go away in the atmosphere. It can persist for a while. And so actually D5-siloxane has been shown to transport over long distances. It's been observed in the Arctic, for example. It's also been observed in aquatic environments, and it is believed to be bioaccumulative. So, for example, D5-siloxane that enters a waterway can be consumed by fish, and then that can accumulate in the livers of fish and work its way up the food chain. So that's been shown in work and more broadly outside of the atmospheric community. Other molecules probably follow a similar emission pattern as D5-siloxane. So locally, these will dissipate on the order of 9 hours. But how these persist in the atmosphere or how these persist in environments more generally really depends on their fate and how quickly they react, whether they're water soluble, and that's something that's more difficult to explain broadly, and kind of depends on a molecule by molecule basis.
We had a couple of listeners ask about any seasonal differences that you've seen in levels of VCPs. Maybe it's related to personal care product use. Could you talk a little bit about seasonal trends?
Yeah, so in T5-siloxane, we actually don't see much of a seasonal trend, and that may be because people are applying their hair care products and deodorants every day. The evaporative properties may not change very much, so seasonal trends can affect the evaporation of these products. But when you apply personal care products, your body's always at 98 degrees if you're not sick and you're feeling good. So they'll evaporate at the same rate regardless of season. We have seen seasonal differences in a paint tracer, for example. So parachlorobenzotrifluoride, as we showed, didn't have a really strong population density relationship, and that was because it's actually more associated with construction. So when we drove, for example, in Chicago, we saw significant PCBTF emissions, and you'd see these emissions spike whenever we drove by a construction site. And so that construction varies, and I don't know necessarily how it varies, but we did see more PCBTF in the summer than we did in the winter, and perhaps that's because there was more construction activity in that summertime period. For the monoterpenes, we see the roughly same urban enhancements of monoterpenes, but again, that gets complicated because in the summer, monoterpenes are influenced also by biogenic sources. So it becomes harder to detect the anthropogenic signal in urban regions in the summer. So that has some complications there. And then other molecules, we didn't see huge differences. So perhaps for personal care products, there's not much of a difference. Construction activity there was, and then there are still questions related to the other types of sources, say cleaning products and whatnot. Perhaps people clean more in the summer than they do in the winter, but we didn't see much of a difference yet, but that doesn't necessarily mean there isn't one.
Thank you. Another question from a listener was, do the levels of monoterpenes in urban areas exceed any levels associated with health effects for these substances? I don't know what's considered the unhealthy level of monoterpenes, but in general, they are comparable in concentration to the natural source that we measured. So in general, no, they didn't exceed very, very high levels, but they're comparable to the natural source. Yeah, and really the question that we have is, how do these affect other pollutants? So monoterpenes are highly reactive, and so they can form ozone. And so the bigger question, and perhaps the bigger concern that we had, is how much do these contribute to ozone formation? And there we saw that they were, on the order of 10% of the VCP ozone. So, the secondary pollutants that these create are more of interest to us than necessarily their individual concentrations. Thank you. Another listener asked, what do you think are the things we need to do to reduce the anthropogenic VCP emissions by 50%?
Yeah, that's a great question. I hate to say what one should do or what one shouldn't do, but personally for me, one thing that I've done is I've reduced my use. So perhaps to my wife's disdain, I don't wear as much deodorant as I used to. And then, other products, cleaning products, for example, I clean with water more than I do solvent-based. So, on a personal level, there's things that I've done. But from a regulatory side, that's certainly that's a great question, and then one that I have to pass off to the folks who know more about that, since I'm sure that's a very complicated and difficult question to answer. But on a personal level, I've used less, but that's a great question. I'll have to punt on that one.
All right. And a related question, would reductions in VCP emissions involve something like different formulations or removal of harmful ingredients, maybe the use of alternatives, like vinegar, for example, for cleaning? Would that help, you think?
Yeah, I think so. That's actually something that the consumer product industry has been doing. So, we talk a lot about, I did talk in this presentation a lot about how vehicles have gotten cleaner, and that was mostly to show you how the VOC mixture has changed such that, vehicles are no longer so big that they dominate the signal that you would measure in an urban environment. They dominate all the VOCs. They've gotten to a point where, okay, now you can start to see these VCPs as being important. But manufacturers have also done a lot of work to reduce their impact in VCPs as well. So, for example, the coating industry has done a lot of work to reduce solvent emissions from paints. So, if you were to go to Home Depot today and order a paint, they'll list on there the VOC content, and you can buy a paint that is a low or no VOC paint. So that tells you a little bit about what could be done. They've done a lot of removing of aromatic content and replacing that with other types of solvents. Acetone is typically added. PCBTF is actually one that's been added, which is perhaps one reason we can see it in the atmosphere, is that it's an alternative to things like benzene and toluene. And so there has been work to do that. So reformulating is certainly one strategy that's been used by the consumer product industry and seems to be effective.
Excellent. Another listener asked, what are some strategies that could be helpful to reduce ozone formation from VCP emissions? For example, is there correlation for plant or tree cover to ozone emissions?
So I think that's a good one. That's a complicated one. There's lots of layers to that. So as I mentioned earlier, how much ozone you get depends partially about how reactive a species is. So when formulators think about the ozone formation potential of their products, they try to replace things that are very reactive, and reactivity translates to ozone formation, with something that's less reactive. So the question before about reformulating is one effort that's been undertaken to try and reduce the amount of ozone that could come from VCPs. In terms of tree cover, biogenic sources create their own ozone as well, and that's largely due to the mixing of biogenic sources with NOx from anthropogenic sources. So I'm not necessarily sure how that would how that might help in that realm, but perhaps it would absorb some ozone. I know that ozone influences plants negatively, so crop yields lower because of high ozone. But that's not necessarily a strategy that you want to use. You mostly just want to reduce the reactivity of your mixtures. So I think the reformulation is as the previous listener mentioned, is one way to do that.
Great. We had a few questions about different health effects that might be associated with exposure to VOCs or VCPs or potentially ozone. Could you talk a little bit about those potential health effects?
Yeah. Is there were there any specific ones related to? Well, I guess I could talk more generally. So, I mean, the health effects of ozone are well studied, and so the EPA has set a standard of ozone of 70 ppb as being what's considered healthy, and many urban regions are trying to reduce ozone pollution by changing by reducing NOx and reducing VOC emissions to try and meet that standard. So ozone, is a very important pollutant to try to control. It's also a very difficult one or complicated one because it's produced through chemical reactions. It's not something that you can just turn off by stopping production of a specific molecule or something like that. So that one's a complicated one. In terms of the hazardous components of VCPs, I'm not really an expert in that realm, and so we know, for example, that benzene aromatics, those are carcinogenic, but those have largely been removed from VCPs. Again, we talked a little bit about how reformulation of paints, for example, was one way of reducing their ozone formation potential, but they were also reformulated in order to remove hazardous components like benzenes, toluenes, etc. So in the U.S., we've done a lot of work to do that. And in general, a lot of these types of products are moving towards water-based formulations, so that water is not hazardous. So that's a great substitute if you can make your formulation work that way. So there's been effort to do that. I'm not really up to date on all the other hazards of VCP components, and I'm sure that folks in the room or on the line, there's probably many more experts on the line than I on that question.
All right, thanks, Matt. I have a couple more questions here. One listener asked, we have some emissions inventories for VCPs. Do you have an estimate of how those inventories might underestimate VCP emissions?
I think that question is better posed to Brian McDonald. I know Havila Pai has done a bit of work at the EPA, has done a bit of work to try and understand how much these might be underestimated. I don't know the number off the top of my head, unfortunately, and I don't want to give a number without really knowing it. But if I can remember from Brian's paper, I mean, I believe it was like close to a 30-40% underestimation. He had to do a bottom-up. He had to change the inventory a bit and did a mass balance approach to really constrain that number. But I don't know it off the top of my head. And if the listener wants to email me, I could certainly point them in the right direction.
All right, thank you. Another listener asked, could you talk about NOx-sensitive ozone generation versus VOC-sensitive ozone generation, and if there's a seasonal connection?
Yeah, that's great. When I know I talked quickly through this, but let me go to that slide. So the ozone formation is a complicated process where you have, there are nonlinearities in responses to VOCs and NOx. And when you're in a NOx-sensitive regime, you can see in this plot on the upper right, this is ozone responses to changes in NOx. And this is again at that 8-hour ozone maximum, where we saw the most ozone in the 3D model. And so the little yellow dot there shows where we are in our measurements, and then if you decrease NOx emissions, you generally decrease ozone. But where you sit on this isopleph is kind of at NOx saturation for this local ozone production. Now this NOx and VOC sensitivity changes as you go downwind, but at the ozone maximum, there's more sensitivity to changes in VOCs than there is to changes in NOx. Now that changes, like I said, as you go downwind, and that's partially because of the influences of biogenics. So locally, within 40 kilometers, you have VOC sensitivity. But then as you continue to go downwind, you tend to have more and more biogenic sources that saturate the VOCs, and then NOx becomes your limiting reagent. And so then as you go further and further downwind, you transition into a NOx limited regime. So one of the components of this change from VOC to NOx limitation is biogenics. So in an area where you have a lot of biogenic emissions, you can be in a NOx-sensitive regime really quickly. If you are in an area that has low biogenics, you may be in an area that's more VOC limited. And this is a question that we were interested in addressing with the upcoming field campaign Aroma. So when we fly to an urban region, let's say Las Vegas, where they have ozone exceedances, there's not a huge biogenic signature in Las Vegas compared to New York City or the East Coast. And so are you in a more VOC sensitive regime, or are you in a more NOx sensitive regime? That's one question we hope to answer. So there can be seasonal differences based off of isoprene. There's also potentially differences in just temperature. So when we were in New York City on July 2nd, that was a big heat wave that affected the entire U.S. region, the whole eastern U.S. seaboard. And it was, like in the high 90s, high relative humidity, and all of that can influence the chemistry significantly. So this picture that we're showing you here could change if you have difference, on a non-heat wave day versus a heat wave. And we haven't probed that too deeply yet, but that's certainly something that can be different. So depending on whether that you're looking at ozone formation on an extreme event or a maybe a typical non-extreme event, that might change the VOC and NOx sensitivity curves.
Great. I believe we have one last question. This is related to attributing different pollutants to certain sources. How would you account for something like limonene creating formaldehyde after it's emitted from certain products?
Sorry, could you repeat that? You broke up there a little bit.
Oh, sorry. The question was, how do you account for limonene, for example, creating formaldehyde after it is emitted from different products?
Meaning in the modeling?
I think so.
Okay. Yeah, so we have limonene specifically, the chemistry of limonene is specifically represented in our modeling efforts. We use a mechanism that's a reduced mechanism, meaning it's not, there are many different mechanisms you can use, but in order to do 3D modeling, you need something that's, that's not too computationally expensive, so we use what's called a reduced mechanism. But for limonene itself is explicitly represented in our model. And so it undergoes many chemical reactions and forms some component of formaldehyde. We haven't investigated specifically the limonene to formaldehyde connection, and we could do that. We could turn off limonene and see how much does this change in our model, the amount of formaldehyde that we predict. I will say that a lot of the formaldehyde that is produced in the model comes from biogenic sources. It's something like 50%, so that's isoprene reacting alongside NOx. That contributes significantly to the formaldehyde that we observe in the New York City region. It's not clear how much anthropogenic monoterpenes might contribute to the total formaldehyde signal, but it's something we could test, and we haven't necessarily done that, but the model is set up to address that question.
Okay, great, Matt. Thanks. I think that is the last question for today. Thank you again for your presentation and for answering everyone's questions. And thank you to everyone online for submitting those. So that will conclude our webinar for today. For announcements of future IAQ Science webinars, we invite you to visit epa.gov/IAQ. Thank you for listening.